All right, I thought it might be interesting to go through the 2014 released AP Calculus, now the AB version of AP Calculus, the released exam. I'm going to go through it in a sequence of videos. Like today, I'm going to do 5 questions from the multiple choice section where it's no calculator. So no calculators on any of these. And on all these questions, I'm going to try to move it along and try to sort of think out loud so that you can be noticing the same things I am as I'm working through. Remember, when you take the real exam, you want to keep it moving so that you get through all the questions and you leave plenty of time for the more difficult questions. Okay, let's get to it. So question 1 here, I see an integral. That means I'm going to be doing the antiderivative. I also notice that the upper bound is a variable. So after I do the antiderivative, remember we represent antiderivatives with the capital F typically. We're going to end up plugging x in, and then we're going to also plug 2 in, and we're going to do subtraction. So we do have to do the antiderivative of this here. So let's do that down below. So we're going to do the power rule in reverse. So we add 1 to the exponent, and then we divide by the new number. So 3 divided by 3 is 1 out front. So I'm not even going to bother writing that. So t to the third there. And then the antiderivative of minus 1 or negative 1 is negative t. Okay, and we're going to evaluate that from 2 to x. So this is where I'm going to go ahead and plug the 2 in. We always plug the upper bound first, x to the third minus x. And you see some of those answers up above have that, right? But don't forget, you have to also subtract capital F of 2. 2 plugged into the antiderivative. So here's the antiderivative, so we're going to put 2 in here and here. So that would be 8 minus 2, which is 6. So we're looking for x to the third minus x minus 6, which is right here, answer A. When you take the exam, try not to write more than you need to. Okay, like I probably wouldn't have bothered writing this. I would have just looked for the answer and moved on to the next question. All right, next question. What is the slope of the line tangent? The derivative comes to mind, right? The derivative is that tangent generator to the graph of the function y equals the natural log of 2x, where x equals 4. So we're going to have to find the derivative, and then we're going to plug 4 into that. That's the two-step process. So the derivative of this, again, on the actual AP exam, don't bother rewriting it. That just wastes time. We're going to take the derivative. The derivative of natural log u is 1 over u, so 1 over 2x. But don't forget the chain rule. Some students will. We're going to multiply by the derivative of that. So then what happens is the 2's cancel. We're left with 1 over x. You plug your 4 in, you get a quarter. A quarter is the answer. All right, so that's like a 20-second problem max. All right, you read it, you see the tangent, you see they gave the function, boom, take the derivative, plug 4 in, you're done. Moving on, number 3, look at this problem. What do you see? I see I'm going to need to take the derivative, and I'm going to need to plug 2 in. So it's kind of similar to the last problem, but who knows? Let's see what else is there. All right, so we got to do the power rule here. When we take the derivative, we get negative 8x to the, all right, here's where maybe some students might make a silly mistake. You need to reduce the exponent by 1 when you're taking the derivative. So that means adding negative 1. So it becomes negative 3 plus, okay, so if you multiply by 2 here, you get 2/4 times x, and then the derivative of 4, of course, is just 0. Now we're going to plug 2 in. So if I plug 2 in here and plug 2 in here, I end up getting negative 8 over 8. Why? Because 2 to the negative third is 1/8. So end up getting an 8 in the denominator here, plus 4 over 4. What do you see? This is negative 1. This is positive 1. They add up to 0. The answer is 0. Hopefully you followed my logic there. I think the trick was that negative exponent, all right, when you take the derivative, it becomes negative 3, not negative 1. And then just the plugging in there. All right, 2 more questions lined up here for you. Once again, an antiderivative. We're taking an integral. This is a definite integral. We have bounds. So we have to find the antiderivative first. And this is a 1 over u question where u is 2x plus 1. So we're going to have to do some quick u substitution. So this is the way I always set it up. U equals 2x plus 1, and then I write du equals 2 dx. So therefore dx is the same thing as du over 2. Notice that 2 is in the denominator. So when I rewrite the integral, I could put a 1/2 on the outside. That 1/2 comes from this guy right here, okay? Because I'm putting that in for dx, as you know. Hopefully this is just all review for you and easy peasy. This is 1 over u du, which is 1/2 ln u evaluated from. Now, you're probably wondering, wait, Mr. White, are you going to change the bounds? Yes, I am. Here's our machine that converts from x's to u's. So I have to plug the 1 in there and the 2. So if I plug 1 in, I get 3. If I plug 2 in, I get 5. So evaluated from 3 to 5 is how you say that. This would be 1/2 times the quantity ln 5 minus ln 3. And if I zoom out here, that is option E. That is option E. It was there. All right, one more question for this video, and then I'll just keep chugging along and make subsequent videos with and create a playlist for you so you can go through the entire test. All right. Oh my goodness. So we have a crazy graph, lots of things going on, and I look at this problem and I see they're testing our understanding of one-sided limits as well as regular old limits. So let's just go through it one at a time. The limit as we approach 2 from the left, well, where's 2? Right here. The limit as we approach 2 from the left is f of 2. And I do see that there's a closed circle here. Both of these are -1. We're approaching -1, and when we get there, we're actually at -1. So that's true. What about 6 from the left equaling 6 from the right? Remember, this is one of those tests for whether a limit actually exists there. Does the left equal the right as we approach 6? It sure does. They're both approaching an output of -1. So once again, -1 equals -1. So that's true. And then on this last one, does the limit exist at 6? Well, let's see. Does the left equal the right? Yeah, we just said they're both -1. But wait, what about f of 6? If you go to 6, you end up going down to -3. You end up going down to -3. This equals -3, so this is not one of the options. And fortunately, it looks like option C includes Roman numerals 1 and 2. All right, so hopefully you found this helpful. Check out my playlist where I just continue on. I'll do 6 through 10 next. All right, good luck. All right, continuing with number 6 on this 2014 released exam. This says take the derivative of a big mess, right? So there's lots of chains here. If you want to think about this, this is sine of x squared all to the 3rd power. And we're going to take the derivative of that. So we throw the exponent out front. The base stays the same. The exponent goes down by 1, so it becomes a sine squared instead of a sine to the 3rd power. But we have to multiply by the chain, which is the sine of x squared here. So we're going to multiply by sine of x squared. So that would be cosine of x squared, but then we have yet another chain, right? When we took that derivative, we have to tack on, as I like to say, another 2x at the end. That's the derivative of that inside function. So I have 6x sine squared of x squared times cosine of x squared. So I scan over here. Do I see that answer? It looks like it is option E right there, option E. All right, moving along. Number 7, limit, a limit. Well, this problem, you can do it 2 different ways. Generally, I know that an exponential wins the game, wins the battle at infinity. So the bottom is going to be infinitely bigger than the top. So I kind of know that this is going to approach 0. But we could also use L'Hopital's rule. L'Hopital's rule says that we can do the derivative of the top and bottom. By the way, because this is infinity over infinity, we're allowed to do L'Hopital's rule. So the indeterminate form, 3x squared over 3e to the 3x, and then we could do it again, equals the limit as x goes to infinity of 6x over 9e to the 3x. I consider this to be kind of wasting time, but that's all right. I want to show you the full solution here. So then we take the derivative again, because it's still indeterminate form, and we get 27e to the 3x. Now we have a 6 over infinity. That's a constant on the top. So this definitely approaches 0, which is the answer on this. Again, I knew that the bottom was going to be infinitely bigger than the top because an exponential beats a cubic every single time. All right, moving on, number 8. All right, we're going to do U-substitution here. They actually tell us what the U-substitution would be. So I'm going to jump in here and write that down. I then take the derivative. du would be cosine, actually 2 cosine of 2x, because you have to remember you have to tack on the derivative of that 2x, dx. So then if we plug it in, dx is going to be 1 over 2 cosine of 2x with a du on the top. So you see we're going to end up with a 2 on the bottom and a cosine on the bottom. So that's why we can rule out these options right here, because I know it's got to be an answer with a 1/2 out front. This cosine, when we plug it in, is going to cancel this one up here. So I've got the integral of u to the 5th with a 1/2 out front. Now, I still have to change the bounds. I have to change the bounds. So I use their substitution. So I have to do u equals the sine of 2 times pi over 2. Well, that's just the sine of pi. And again, I would not be writing all this if I were taking the actual exam. I'd be kind of thinking it through. The sine of pi is 0. Okay, so the upper bound is 0. So the answer has to be D, because the other ones don't have an upper bound. But let's just check our work. Let's keep going. The sine of 2 times the lower bound was pi over 6. That's the sine of pi over 3, which indeed is radical 3 over 2. So option D is the answer. All right, number 9. A function has a derivative given here. They've given us the derivative. We don't have to find it. At what values does x have a relative maximum? So we're looking for something like this, where we change from increasing to decreasing. Okay, so what we do is we find the zeros first of all. We set this equal to 0. That happens at x equals 0, x equals 3, and x equals -1. I'm then going to do a sign chart. I like to do them different ways, but this is one way to do it. -1 up to 0, and then 3. Okay, and then we have infinity over here. So this represents 3 to infinity. This is -infinity to -1. So I have to do a sign chart where I decide whether it's increasing or decreasing. So if you plug negative bazillion into this, you get a negative times a positive, because when you square anything, you get a positive, times a negative. That's a positive, so we're increasing there. And then between -1 and 0, for example, maybe -1/2. -1/2 would be a negative times a positive times a positive this time. So negative, so decreasing. So right there we have a max because we're doing this, but let's keep going. Now pick a number between 0 and 3. How about 1? If you plug 1 in, you get a positive times a positive times a positive. That's a positive right there. Okay, and then if you plug infinity in, you're still increasing. So the only maximum is at -1. -1. All right, on this last one, this is an interesting question. it says we want this function to be continuous. All right, in order to be continuous, our limits have to be approaching left and right, and we have to be there also. Okay, so the limit as x approaches 2 on this thing right here has to equal where we really are at x equals 2, which is b. Now, if you factor this, this is x minus 2, x minus 5. Okay, we can then cancel these and rewrite the limit like this. X minus 5 over b has to equal b. You can then plug the 2 in there, and you get negative 3 over b has to equal b. If you multiply both sides by b, you get b squared is negative 3. That's never going to happen. You're never going to have a negative generated by a square. So there is no such value b. All right, we'll see you on the next video. All right, let's continue our adventure into that 2014 released AP exam. I've got questions number 11 through 16. Remember, these are the no calculator questions. So on this first question, first of all, if you look at this, it says the graph of f prime. This is not the graph of f, it's the graph of the derivative. Always know what graph you're looking at. Okay, so this says from 0 to 6, we're looking at this thing, the derivative of piecewise. We see the pieces there, of course. Now it says that the original function starts at 1. At time 0, it's at 1. So what is the maximum value of f on the derivative? Now if you think about a number line, this is what I'm kind of picturing here, is at time 0, we're actually at 1 to begin with. This is at t equals 0. Now I look at this graph and I see this section of the derivative is positive. What does that mean? That means movement to the right. So for the first 3 seconds, this object is moving to the right. So this over here will be the maximum value then, because then it's going to move to the left and then back to the right again, and then a little bit more to the right. But the max value will happen at 3. I think that's pretty clear. And here's one of the tricks. One of the ways to do this is to find the area of that triangle. Find the area of that triangle, and that's going to be your net change. This will be the total change is the area under there. Well, the base here is 3. The height is 2. So 3 times 2 is 6, and then of course you have to divide it by 2 because it's a triangle. So we get a net change of 3. Now remember, we started at 1, so we moved all the way to 4. And 4 is the example. That's when it's at its highest value. And again, I knew that because the derivative is positive, which means the slopes are positive, which means it's going up or moving to the right, increasing on that number line. Okay, number 12. We have a function given by 9 to the x. If 4 subintervals of equal length are used, what is the value of the right Riemann sum? Okay, so we're going to divide this into 4 subintervals. So from 0 to 2, okay, that would be 2 subintervals. Now if I insert a 0.5 there, and I insert a 1.5 there, now I've got 1, 2, 3, 4 subintervals, right? Now we're going to create rectangles, and we're going to figure out the areas of all those rectangles. And the height of the rectangle will happen on the right-hand values, of this. So if you notice, each subinterval is 1/2 in width. These are all 0.5. So we're going to have 1/2 times, now we could do 1/2 times the height, 1/2 times the height, 1/2 times the height, or we could make it a little faster and we could use the distributive property to our advantage. So this is going to be f of 0.5 plus f of 1 plus f of 1.5. And if I were actually taking the exam, I probably wouldn't write this out. I'm just trying to help you understand what I'm doing. So I'm going to find these heights by putting 0.5 into the original function. Right? So this is going to be 9 to the 1/2 power. This is going to be 9 to the first power. 9 to the 3/2 power. You'll see why I'm writing it that way here in a moment. That's 1.5 plus 9 to the second power. All of that will be multiplied by 0.5 or divided by 1/2, or divided by 2, I mean. All right, this is the square root of 9, which is 3. 3 plus 9 plus, or this is the no calculator section. How can I do 9 to the 3/2 power? 9 to the 3/2, if you remember, is really the square root of 9 to the third power. What's down low is your root number, as I like to tell my students. So this is 3 to the third, which is 27 plus 81. So if you add all these up, this is 12. 12 plus 27, that's 39, plus 81 is 120. But don't forget, we have to divide it by 2, and we get 60. So I'm sorry for the chicken scratch, just trying to move along as you might do on the AP exam. So the right Riemann sum would be 60, and that's the answer. All right, moving on to 13. This is actually a pretty easy one because I'm sure you have that quotient rule drilled into your head, right? High and low, and the quotient rule goes like this. It's low d high, that's the derivative of the guy up top, and that's a 1, minus high d low, and the derivative at the bottom is 2x all over the denominator squared. And you see this is starting to look like some of the answers down below, but we got to do the algebra up here very carefully. We don't want to mess something up right here at the end and then end up missing it. That would be very sad. X squared plus 1 minus 2x squared plus 2x all over x squared plus 1. There's a fine line between being careful and also moving it along. We distribute this and we get negative x squared when you combine them. So I am kind of skipping a step here. Negative x squared minus 2x plus 1, if I put it in standard form, all over x squared plus 1, all squared. And I think that answer is there, isn't it? You see it? It looks like it's C. C. All right. We've got a few more problems lined up here. All right, the velocity of a particle moving along the x-axis, so it's moving left and right because this is a sinusoidal function, so it's going left and right. Its velocity is positive for a while, and then it's negative, and so on, at time t. If the particle at x equals 4 when t equals 0, so that means it's starting at 4. Don't forget that, it's starting at 4. What is the position of the particle? So S of 0 is 4. That's going to allow us, if you remember, that's going to allow us to solve for C. This is going to be one of those initial condition problems. So the position function is the antiderivative of the velocity function. So we have to do the antiderivative, and then we're going to solve for C. So if you do the antiderivative of this, it's a quick little U-substitution, and you end up getting negative cosine of 2t. But don't forget, you're going to have that u equals 2t. So you're going to end up with a 1/2 out front when you divide both sides by 2. All right, try the U-substitution, and you'll see what I mean on that. Plus c equals the position function. All right, now they gave us one of the data points. They said 4 is the output when you put 0 in here, and of course 2 times 0 is 0, plus c. What is cosine of 0? Again, no calculator section, so you're supposed to have that memorized. That's 1. So we then add 1/2 to both sides. We see that c is, I'm going to use decimals here, 4.5. C is 4.5. So I'm going to rewrite the function even though on the AP exam I would not do this. 2t plus 4.5. All right, so what does the question ask you to do at this point? Plug pi over 2 in there. So what happens is the 2 cancels with the 2, and you're left with cosine of pi, which is what? That is -1 times your -1/2 is actually +1/2 plus the 4.5 here is 5. 5, the answer is D, 5. It started at 1, and then it moved to the right all the way to 5 at that point in time. All right. Okay. I actually misspoke. It started at 4 and it moved to 5. There we go. All right. All right, 2 more problems on this video. This was a really interesting question. I like this one a lot. The function g of x is differentiable and increasing. So when I read this the first time, I thought, okay, that means g prime of anything is always positive for all real numbers. Okay, so it could be for anything. We'll get to that in a second. On what intervals is the composite function, where you have this cubic on the inside, also increasing, or when is it going up? Okay. Well, I think we need to take the derivative of that guy. We need to take the derivative of the composite function and see what happens. Because that's when they're asking is, when is g prime of x third minus 6x squared always positive? That's what goes on in my head. I got to figure that out. So I'm going to take the derivative. What is the derivative of this when you have a composite function? Don't you always take the derivative of whatever you have? This is what we have. It doesn't matter that we don't know what g is. Okay, we take the derivative of it, but we have a chain. We have an inside function. So we multiply by the derivative of what's inside. That would be 3x squared minus 12x with a parenthesis around it. Right? This would be what g prime of x to the third minus 6x squared would be. All right, hopefully that's making sense here. All right, now this right here is always positive. Why? Because of what they told us earlier. They said no matter what you plug in g prime, you always get a positive number. Always, always, always. Now this part over here is a quadratic, and I'm going to just factor it. I'm going to factor 3x out, and I get x minus 4. So that means x equals 0 and x equals 4 are what we call zeros. And as you recall from algebra class, this is a parabola. The graph of 3x squared minus 12 would look like this. One thing in AP Calc is you always need to think graphically at the same time you're thinking numerically and algebraically and all this stuff. So look at this. This right here is when it's negative. This is when it's negative from 0 to 4. From 0 to 4 is when that's negative. So the question that it was asking is, when is the g prime of that mess, when is it positive? Well, that would be only when we have a positive times a positive. A moment ago I said this first thing is always positive, so we're good there. So when is this parabola positive? On this interval and this interval. That's why the answer is A. That answer is A. So this was a test of your understanding of the chain rule, and that we really didn't need to know what the g function is. We just needed to multiply by the derivative of that inside function at the end. All right, we got one more question here, and another good one. What is the limit involving an absolute value coming from the left? So that made this interesting. So you understand that x minus 3 with an absolute value looks like this. It's a shift to the right by 3. Right? So if we're coming from the left on this quotient function, we really only have to consider this side of that numerator function. Right? So this is really a piecewise function. To the left of 3 and to the right of 3. Those are the two pieces. And this question is only asking us about the left side. So I can literally replace it with this line. This is y equals negative x plus 3, because this hits at 3 and it has a slope of negative 1. You see that? It hits at 3 and has a slope of negative 1. So I can put that up here, negative x plus 3 all over x minus 3. I then factor in negative 1 out of the top, and I get x minus 3. X minus 3 was already on the bottom. These cancel. Remember, you can always do algebra magic, algebra canceling and manipulation on limits. So now we have the limit as x goes to 3 coming from the left of a constant is just the constant. So that's the answer, letter B. All right, so we'll continue on with question number 17 in the next video. Good luck. Hope this is helping. All right, so we're going to continue along with this 2014 released AP exam, AB. We're going to do numbers 17 through 22 of the no calculator section of the multiple choice. On number 17, we're finding the derivative, it says, of this exponential function with base e. And notice we've got these generic numbers a. So just think about them as being like a number, like 4, 5, or 6, and how would you do this? So the derivative of e to the u is just e to the u. So the derivative of this would be a e to the negative ax, just completely unchanged, but you always multiply by the derivative of the inside function. So here's the inside function. So if we multiply by the derivative of that would be negative a, right? If that were negative 5x, the derivative would be negative 5. So we end up getting negative a squared e to the negative ax. So that's the answer right there. Really easy one. You should be able to do that one pretty quickly if you just recognize a is just a number. Okay, here we go. Number 18. A student attempted to solve this differential equation with the initial condition 2 and 0, so 0, 2, for example. At which step did they mess up? So remember, when you solve a differential equation, you separate the x and y. So the y goes over with the dy by dividing both sides by y. That's why it landed on the bottom. And on the right side, I end up with x dx. And then you're going to take the antiderivative. And that's what they've done there. And that all looks good. Now, in step 2, what they've done is they've done the antiderivative. So this would be ln absolute y equals 1/2 x squared plus c. So that all looks good. They did the power rule in reverse, and of course the antiderivative of 1 over y is ln y with the absolute value. Now what did they do? They got rid of the natural log by basically putting a base e on both sides, but they didn't quite do it correctly. This plus c shouldn't just be slapped at the end because of the, look what I did here. It actually should be up in the exponent, or if remember when you're adding exponents like that, it's the same thing as multiplying. So you could think of that as e to the c being up there. So right there was the mistake, because if you plug y equals 2, by the way, this is equal to, so then if you plug y equals 2 in there, and x equals 0, you get e to the 0, e to the c. Now this is just 1, so e to the c is 2, so that means c equals the natural log of 2. not what they have there. So it really went wrong on step 3, and B is the correct answer. All right, moving on to the next one here. For what values of x does the graph have a point of inflection? So ask yourself, okay, so what do we look for here? We look for when f double prime changes sign. So if it changes from negative positive or positive negative, that's how we know we have a point of inflection, when the concavity changes, and the second derivative is where concavity comes from. So we got to find the second derivative, so let's do that. The first derivative would be 15x to the fourth plus 40x to the third. The second derivative is 60x to the third plus 120x squared. You know, this is the no calculator section, so you kind of hope that the numbers are going to work out nicely. You now factor it. 60x squared gets factored out. That leaves x plus 2. So the critical points that we need to look at where we think just maybe there's a point of inflection would come from x equals 0 and x equals negative 2. That's the 0 on there. Now I like to do a sign chart like this where I have my critical values and then I have my intervals that I'm going to look at. All right, and we're going to look at f double prime. So you can come back right here. Imagine plugging negative bazillion in here. This term is going to win, and it's going to be negative. So this is going to be negative. If you plug positive infinity, we're going to end up with positive. So we really need to know what's going on in this interval right here. I like to plug negative 1 in. That's the easiest thing. So let's come up here. 60 times negative 1 to the third power, that's just negative 60. And then, of course, anything squared is positive. So plus 120 times negative 1 squared is plus 120. That is positive 60. All we care about is the sign. So this is concave up there. The original function is concave up. So we have a point of inflection at negative 2 only. Negative 2 only. That's where the sign changed. Didn't really care about analyzing that first derivative here. Number 20. Number 20. Which of these is the right answer? This is kind of a crazy one. You look at it for a little while, limit, you can't plug 2 in here because you get an over 0 problem. Now you can plug, you can't plug 0 in the top either, right? Can't plug 0 in the top either because you end up getting ln 5 minus ln 5. That's just 0. So how do you deal with a situation when you have 0 over 0? That L'Hopital's rule. L'Hopital's rule says that you can take the derivative of the top, the derivative of the bottom, and evaluate on the same limit. So here we go. What's the derivative of natural log x plus 3? By the way, we're not doing the quotient rule. We're taking the derivative of the top and the bottom separately in L'Hopital's rule. Okay, so no quotient rule here. I don't know what made me think about that, but we do not do the quotient rule. So this would be 1 over u, right? So 1 over x plus 3. There is no chain to tack on. Minus the derivative of a constant is just 0. That's nice. And then the bottom, the derivative of x minus 2 is 1. Now can you plug in 2 safely without any divide by 0 problems? Hey, you bet. We plug it in there, we get 1/5 minus 0 all over 1 is just 1/5. That's the answer. That wasn't so bad. It looked kind of crazy at first. All right, moving on. Number 21. We have functions w, x, and y, and they're all differentiable with respect to time. Uh-oh, it sounds like a rate of change problem. Okay, our related rates by the equation w equals, okay, so we've got this here, w equals x squared y. If x is decreasing at a rate of, okay, so that's why I write dx dt. I always use the Liepniz notation. Decreasing means it's going down by 1. So I convert it to Liepniz notation as I'm reading it. Okay, and then it says, and y is increasing, so that means dy dt is going up by 4. At what rate of change? So they're asking dw dt is what? That's what we're going to solve for here in a moment. When x equals 6 and y equals 20. All right, so I really encourage you to try to jot things down like I did off to the right there on the screen. And then let's take the derivative implicitly, like you learned how to do in the related rates. So we start with that. So if we take the derivative, we would get dw dt, whatever the derivative is with respect to t. Now on the right, what do we have there? Let me hear you. The product rule. That is a product. Careful about this. So we take the first times the derivative of the second, which is just dy dt, plus the derivative of the first is 2x, but, x is a function, remember, so you have to put a dx dt there. You probably know that. I'm just making sure you remember. And then times the second. So that is just the product rule. Product rule. And we have everything. We have x equals 6, so this would be 6 squared. We have y equals 20. This would be a 20 over here. 2 times 6. And then off to the right here, let me bring it back to the screen there for you. We have that dx dt is -1 and dy dt is -4. We wrote that down a moment ago. So we put the 4 here. I think I said -4, but it's +4. It's because it's increasing. So dy dt is +4. Dx dt is -1. All right, so this is 36 times 4, which is 144. This is going to be minus because 2 times 6 times -1 is minus, this is 36 times 4. Let me check this again. 144 minus, we have 2 times 6 times 20 is minus 240. I don't know what I was thinking there. I was thinking 120, but there we go. 144 minus 240 is -96. And that's the answer right there. All right, so the no calculator section kind of tripped me up there for a second where I had to make sure I didn't make some silly mistakes. So you do the same. Just be careful with your arithmetic. You don't want to do all the calculus right and then mess up there. One more question on this video. This is a little bit of a longer one. Let f be the function defined. We've got a cubic. When is it decreasing? Okay, so what are we looking for? So the function f will be decreasing when the first derivative is negative. And also the original function is concave up. So that's so it's going to be concave up when the second derivative is positive. So we're going to have to do both derivatives. We're going to have to do sign charts on both of them and figure out the overlap. That's the strategy. You kind of have to have a game plan going into these, right? So let's get the first derivative. Let's just deal with the first derivative first. That would be 6x squared minus 6x minus 12. I go ahead and factor because I see what's going to happen here. I can factor this into x minus 2, x plus 1. So I see x equals 2. These are my critical points. X equals 2 and x equals -1 are my critical points. So we come over here, and some of you like to use a number line. Let's do that. Here's 0. Here's 2. Okay? So from -infinity, over here, -infinity, all the way up to -1, let's plug in and see. -infinity squared is positive infinity. So you know what? That's going to beat everything out, and we're going to end up being positive. Let me use a different color so it stands out. Positive over here, and positive up here, of course. You know, when you plug positive infinity, all we have to do is check in the middle, and if you plug 0 in, you get -12. Aha, -12. So we're looking for when is the first derivative negative. So far we have -1 all the way up to 2. we still have to look at the second derivative to see where the overlap is on that number line. So let's come over to the side here. I'll do this in a different color. We'll use red over here. I'm going to do the second derivative so that I can do a sign chart on that. That's 12x minus 6. If you factor that, that's 6 times the quantity 2x minus 1. If you set that equal to 0, you see x equals 1/2 is the critical point. So on our number line, negative infinity all the way to infinity, here's 0, here's 1/2. So let's plug negative bazillion into this. Do you get negative or positive? You plug negative 1,000,000. Negative. Okay, so that means concave down, concave down, concave down right there. And what about positive infinity? Of course, it's plus, so it's concave up there. All right, so let's go. We just figured out that when we're looking for concave up, right? So we want to know 1/2 and higher. So if I come over here, here's a half, 1/2 and higher. So where is the overlap? Where were we decreasing but concave up? I'm trying to get my highlighter here. It's right in this region, right in that region. From 1/2 to 2 is when this thing is concave up and decreasing. Because over here we figured out from 1/2 to infinity, it's concave up. So the overlap is in this region right here that I've highlighted. And that is 1/2 to 2. Is that one of the answers? It sure is D, and that's the correct answers. All right, we got one more video to finish out the multiple choice without the calculator. All right, good luck. All right, we have one more chunk of questions here, 23 through 28. This is the 2014 released AB exam, and we're just right now doing the no calculator multiple choice questions. So in number 23, it gives you a piecewise function. It's in two different pieces, and do you notice that something crazy happens at -1? It moves from a line to a parabola. All right, so if f is the function defined above, then the derivative there is. Okay, now let's think about this. Derivatives don't exist at corners or cusps. So we have to make sure that the slope is nicely transitioning. So the slope on the left has to equal the slope coming from the right. Right? So the limits on the derivatives have to also equal. So what I'm going to do, let me switch back to red here for you. I'm going to find the derivative of that left-hand region. It's the left because it's x is less than 1. And then on the right, the derivative would be -2x. Then I'm going to plug the -1 into both of those. So f prime of -1 would be 3. That's coming from the left. I'm not using the proper limit notation here because I'm trying to move this along, just like you would during the regular exam. If you plug -1 in here, you get 2. The slopes are not approaching the same value, so this is a corner, so therefore the derivative doesn't exist there. All right, moving on. Let f be this crazy function here. This is called a rational function. Which of the following is a horizontal asymptote? Now don't forget, horizontal asymptotes are all about the limit as x goes to infinity or -infinity. So when that's the case, you have 3 options or 3 cases to consider. If the degree on the top is bigger, there is no horizontal asymptote. If the degree of the exponent, the net exponent on the bottom is bigger, the answer is horizontal asymptote at 0. But in this problem, it's a little different. We have a square on the bottom, and we would have a square on the top. If we multiply that out, if we FOIL it out, we're going to get, and I'm not going to do the whole thing, -12 x squared would be my term on the top. You see that? And then my term on the bottom would be 4x squared. Now there'd be extra funny business here, but as you know, when you're plugging infinity in, those don't matter anymore. So when the degree on the top is equal to the degree on the bottom, you use the ratio of the leading coefficients. So the answer is there's a horizontal asymptote at y equals 3. So that turned out to be a pretty easy problem as long as you knew what the definition of a horizontal asymptote involves limit as x goes to infinity, and you also realize that the degree on the top and the bottom are the same, and there's no reason to multiply that out. Don't waste your time, folks. Just those first two terms are all that matter. All right, so here we have a function according to x, and then a function u according to x, and they want you to relate those two, dy to du. So this is going to be dy dx times dx over du. All right, so we're going to need to get dy dx. That would be 2x minus 2. And then du dx, right, the derivative of u with respect to x would be 2. Now we flip it over. We flip over that du part. We flip that over, and it becomes a half there. And then we bring our 2x minus 2 in there. That ends up being x minus 1, which is the answer. All right, the next one. You look at this and you, oh my gosh, this looks crazy. Look at the bounds and, oh my gosh, is this like inverse tangent or something? What do you notice? This is just the derivative of an integral. They undo one another. The derivative of the integral, they just undo one another, and wherever you see the t, you put that upper function. It has to be on the upper bound, by the way. But that's an inside function also, so we got to do chain rule. It's an inside function. So we tack on, we multiply by the derivative of the square root of x. Now remember, the square root of x, you should probably memorize this derivative, honestly. Okay, so then if you take the derivative of that, if this is f, f prime would be 1/2 x to the negative 1/2 power. That's 1 over 2 radical x, 1 over 2 radical x. So the final answer is 1 over 2 radical x and then 1 plus x. That, because when you square a square root, you get that. So do you see that answer there? I do. I see it right here on A. All right, cool. So I think a lot of students would accidentally say C because they would have forgotten to tack on that derivative, to multiply by the chain. That's really important. We got two more questions. A particle moves on an x-axis left and right according to this lovely sinusoidal function over here. When is the particle at rest? Okay, so what are you thinking? Velocity has to be 0. Velocity has to be 0 for this thing to be at rest. So we better take the derivative of the position because that's velocity, right? So velocity function would be 2 pi cosine 2 pi t. You notice that chain that I put on the front? This was the chain rule of that inside function right there. Plus the derivative of 2 pi t according to t, with respect to t, would be 2 pi. Now we want to know when this thing is 0, so we set it equal to 0. So we have 2 pi cosine. We always try to move as quickly as you can. Be careful with your algebra. We subtract the 2 pi to the other side. Okay, I'm going to show my work here, although you might actually skip this step. Because at this point, you're going to divide by 2 pi and get negative 1 equals cosine of 2 pi t. All right, when is cosine negative 1? Well, I think about the graph, and I think about it bottoming out right here at negative 1 after pi radians, right? Because it's a 2 pi period. So I want to know, when is this equal to pi? Because that's when we'll have the cosine of pi equaling negative 1. So I set that equal 2 pi t equals pi. I divide both sides by 2 pi. Pi's canceled. T equals after 1/2 of a second. 1/2 of a second there. All right, one more question and we're done with this section. Now this may make your head hurt a little bit. These slope fields, these can be a bit tricky. Really, you want to look for symmetry. You want to look for symmetry. Like, for example, I notice right here that, by the way, this is 2, this is 1. So at y equals 1, x doesn't matter, first of all. So you see how it's completely dependent of x. And I also notice that the slope there is 0. In other words, dy dx is 0 whenever y is 1. And I look down here, and I can rule some of them out. You see, this letter C is dependent on x. When y is 1, we'd have different slopes. That's not correct. Same thing here. If you factor the x out, you get y plus 1. 1 is not going to cause, y equals 1 is not going to cause a 0 there, so I can rule that out. Now up here, if I factor the x out, I get y minus 1. If you plug 1 in there, you get 0. If you plug 1 in right there, you get 0. So we can't rule a out. Same thing for d and e. We can't rule them out. All right, so what do we look for next? Well, what I look for is that when y is bigger than 1, I notice, and by the way, and x is positive, I notice that we're getting positive slopes out of that. So when y is bigger than 1, and when x is positive, we get positive slopes out of it. So let's see. When y is big and x is big, we get positives. Yeah, that works. So this one is still, a is still in the mix. All right, what about this one here? When y is positive, real big, and x is real positive, we also get positives. But then I realize something on letter D. I realize that it has an x squared in it, which means it doesn't matter whether you go left or right, you would get the same slope. Let me say that again. It doesn't matter whether you go left or right, you would get the same slope. So we ought to see symmetry left or right. So this thing ought to equal whatever's over here. This thing ought to equal whatever's over here, and it doesn't. So I can rule out letter D just from my understanding of symmetry. And then I'm on a roll with symmetry, and I'm realizing this one is not dependent on x at all. There's no x. There's no x. So if there's no x, what happens in the slope field is they will all be the same like this if there's no x, because it's not dependent on x, and that's not the case here. All right, so I've kind of ruled them all out, and I've got my answer as being A, and you can start to do this analysis here and start to see how this one continues to work in all 4 quadrants of this graph. 1, 2, 3, 4 regions of the graph, and you can check just for signs, the SIGN, of course, of the different slopes, and it'll work. All right, so that was a tough question, took quite a bit of analysis there, but hopefully if you moved along during the previous problems, then you would have plenty of time to tackle some of these more difficult ones. All right, I'll put together videos on the no calculator section, or I'm sorry, the calculator section, and that'll be exciting too. All right, good luck. So we finished the no calculator section. Now it's time to go through the calculator section. Now, I will tell you, only about a third of these problems really need the calculator, so that's something to keep in mind. So if you're not needing to use the calculator on a lot of these problems, you're not doing anything wrong. So let's dig in. We're going to do about 5 or 6 problems here in this video. It looks like there's 17 questions in this section, so I think I'll split it into about 3 videos to go through all these clearly for you. On this first one, it says an object is moving along a straight line for positive t, of course, where the position is s, the velocity is v, and the acceleration is a. They're just giving us definitions there. We don't know what those functions are. Which of the following expressions give the average velocity. Average velocity over time. Well, average velocity is simply your change of position over time. It doesn't really matter what happened in the middle as far as position goes. All right, we're just going to map a secant line from start to finish and find the slope of that. So this happens at 8. This happens at 2, right? It says this is happening from 2 to 4. So the position would be s of 8 minus s of 2, right? That's the change in position, all according to 6 seconds. So no calculator needed in there, that's for sure. Okay, moving along. If the sine function is the antiderivative for f, then the integral from 1 to 2 on f would be, well, you see here, we don't have to do the antiderivative because it's already been done for us. So this would be sine of 1 over x squared plus 1 evaluated from 1 to 2. Now this is a good moment for me to say, and I'm sure it is, your calculator needs to be in radians mode for all of this. For the entire AP Calculus test, it should be in radians mode. All right, now we plug in our upper bound. That would be 1/5, right? 2 squared is 4, 4 plus 1 is 5, minus the sine of 1/2. All right, and now we will need to go to our calculator. So I've got a TI-84 emulator here, so I can show you. We're going to do sine of 1 divided by 5 minus the sine of 1/2. And we hit enter, negative 0.281. And the answer is right here, isn't it? So 77 is A. All right, moving on. That's the right answer, by the way. I was looking at the key just to triple check for you. The function f is differentiable. Okay, so that means the derivative exists everywhere. So if you look at all these, it's these graphs, these are not undefined anywhere, by the way. Okay, the graph of f has exactly 1 point of inflection. And, by the way, it's also increasing. So what I would suggest when you see it, when it says f is increasing, just write this down immediately. The first derivative is always positive. Okay? Now, what happens at inflection points? At inflection points, it says we have exactly 1 inflection point. So my brain thinks, all right, so the second derivative is 0 or undefined at 1 point. All right, so I'm thinking about all that. Now, we can rule out 3 of these graphs already. Which 3 can we rule out? Well, since they are asking which of the following could be f prime. So these are all f prime graphs. There's only 2 that are completely above the x-axis the whole time. That has to do with this guy right here. So it says the first derivative is positive. So we're looking for graphs that are in quadrants 1 and 2 only. Now it says the second derivative, which would be the slopes here, is 0 or undefined at only 1 place. And I see right here, this is undefined right there. So I'm thinking A is the answer, but let's look at E. Indeed, look, E has it has at least 2 horizontal tangents. So that would be 2 critical points where the inflection could change. So it's definitely A. A is the answer. So we'll get rid of that. All right, so 78 is A. No calculator on that one either. A vase has a shape where it is a function revolving around something. So here's the curve from 0 to 5, and it's revolving around the x-axis. Now, the sine curve, of course, looks like this, right? Because I had to shift it up by 2. And we're going from 0 to 5. So that would be about right here. It doesn't really matter where you put it. And we're going to revolve that around the x-axis and create this vase thing. All right, it doesn't really matter doing a good drawing, but you get the idea. We're going to integrate, and we're going to use the disk method. So all of these are little bitty disks, and each volume would be pi r squared times your dx, right? That's the thickness of each cylinder, and of course you're going to add them all up. That's what the integral does. So you learned all this earlier in the year, so we're just going to integrate from pi radius squared. So the radius in this problem, this is a dx problem because the radius runs up like this. The radius is your y value, and your y value is your function. You did some of these where they revolved around the y-axis, and then it was a dy problem. But this is a dx problem, so we put that in there. So we have to run this through the calculator is the easiest way to do this. Don't try, you might hurt yourself if you try to evaluate this integral without your calculator. So you do math. Number 9 is finite integration, and the lower bound is 5. The lower bound is 0, the upper bound is 5. And inside here, we do have to open a parenthesis because we're going to type 2 plus sine. Oops, I didn't get my 2, did I? Let me go back. All right. All right, so I'm going to second insert. I'm going to insert my 2 there. There we go. And I got an x here. Now remember, I need to close my parenthesis at this point and square that function. Now, I seem to have lost my x again. This emulator is not playing nice. Insert, I'll just use the button. There we go. Did I type it in right? I think I might be missing a parenthesis right here. Second insert. Let me do a parenthesis there as well. There we go. Now we're squaring 2 plus sine x. And of course, this is a dx problem. Make sure you don't just square the sine function. You need to square that entire parenthesis. All right, and I got 25.502. Now that is there, but I forgot something. Does anybody know what I forgot? I forgot to multiply by pi. So let's go back up here, and let's edit this and put a pi in the front. Second insert, and I hit the pi button. Where is that again? There it is. Second, I'm used to the TI-30s because I teach Algebra 2, so don't use these fancy calculators very much. All right, 80.115. Now I'm glad I remembered that 3.14 because wasn't that sneaky? They put that answer there. And if you had accidentally forgotten the parentheses, I'll tell you, this answer would have come up. So they had a lot of good distractors there to distract you from the answer. All right, number 80. The table above shows selected values from a function. The function is twice differentiable, where the second derivative is positive. Okay, what does that mean? So you should write concave up like a cup, right? Concave up like a cup. So we've got, let's just draw a really quick sketch. Here's 1, 2.4. Here's 2, 3.6. And then at 5, 1, 3, 5, it's actually considerably higher. It goes up by 2 instead of just by 1 or so. I'm just estimating here. So 5.4, it's way the heck up here. So this thing is definitely concave up the whole time because of this right there. Okay? It says which of the following could be the value of f prime. So let's find the slope of f prime at 3. They're wondering about the slope of right there. What would the derivative be right at 3? So let's find the slope of the secant line. So that would be 5.4 minus 2.4 all over 5 minus 1 is 3. Okay, so we get, I'm sorry, it's 4. 5 minus 1 is 4. And we get 3/4, which is 0.75. So that slope is 0.75. And if you reason it out, which of these is closer? It's the 0.7, and that is the correct answer. And you can also analyze the slope here. I'm sorry, the slope from, let me change colors. You could analyze the slope from here to here and compare it to here, and 0.7, all signs point to 0.7 is the best estimate. But just doing that slope of the secant line was enough here to get us the correct answer. All right, let's do this one more problem. At time 0, a forest preserve is starting with a population of 1,500. So in your brain and on your paper, you may want to just write this, like don't forget to add 1,500, because the rate that it's growing is given by this function. This is a rate function, kind of like a velocity function. What is the population? So we need to add the change, the total change. Remember, that's the integral of the rate. Like the integral of velocity is can be your distance traveled if you do the absolute value. So this total change would be the absolute value. And I don't need to put the absolute value here because we understand that e to the x is always positive. That is something you might want to think about. We don't need to do an absolute value here, but we could do 2,000 e to the 0.23 t dt. And this is going from 0 to 3. Now, of course, you could do this integral pretty quickly since the integral of e to the u is just e to the u, right? And then you have to take into account the chain, which we do have here. But you know what? I think it's still going to be faster to just plug this in. So let's do that. Let's go back to the calculator. We'll type 1,500 plus so that we do not forget that. And we're going to do math. Finite integration is number 9 there. Our lower bound is 0. Our upper bound is 3. We're not going to forget that 2,000. We've got e to the 0.23. And we put our variable up there in the exponent. And this is a dx problem. So I think I've got that all typed in. And the answer is 10,141. And I'm checking the key. That is correct. All right, good for us. All right, I'll continue on in the next video with number 82. Good luck. All right, let's continue the adventure going through the calculator multiple choice section of this 2014 released exam. Number 82, it says the figure above shows the graph of f prime. Okay, so that's the derivative of f. All right, from -6 to 8. So 1, 2, 3. Let's make sure we've got these labeled just so we're certain. There's 8, and then -6 is right here. Okay, so we're good. Of the following, which best describes the graph of f? Now remember, this is f prime, f prime. So we're looking for mins and maxes on f. Well, what happens there? Isn't that first derivative is either undefined or 0? So we have some opportunities where, just maybe, we have a max or min. Now, does that change sign there? Yes, it sure does. So f is increasing up to here because that graph is above the x-axis, right? And then f is decreasing here. Well, what do you know? That would be a max right there. Now, the first derivative that we're looking at is 0 here, but it does not cross through the x-axis. It doesn't change sign. So the function f is still decreasing here, but then look right here. It does change to, f changes to increasing again. So we're decreasing and then increasing right here. I didn't draw that very well, but you get the idea. That would be a min. All right, so we've got one max and one min. So we're down to either A or B. Which is it? So the next part of this is inflection points. How do we find inflection points? Inflection points come from when that second derivative is either 0 or undefined. And I'm looking at this. It happens at 3 places, it looks like. Definitely here. Definitely here. I think it looks like it goes horizontal here. But remember, the second derivative involves slopes. So right here, the second derivative is negative, and over here it still is. So did we change concavity at -4? No, we didn't. Because the slopes are still negative, the slopes represent the second derivative because we're looking at the first derivative. All right, so let's keep going. Here let me use my highlighter a little bit more exaggerated. Right here, we have a negative slope and we do change to a positive slope. So all of a sudden, the second derivative has crossed through the x-axis. It's now positive. So that would be an inflection point right there. And same thing here. You see how we end up going, we're negative and then we're positive again. I forgot to label one right here. We have another horizontal tangent right there, right? And indeed it does change from positive to negative. So we have an inflection point here. We have, this is becoming a mess. Hopefully you're following me here. We have an inflection point here, here, and here. And it's because the slopes have changed signs at those horizontal tangents. So the answer is A. The answer is A. It's not 4. Some students would say 4 because of this horizontal tangent here, but this was not an inflection point. Hopefully that all made sense. Moving on to number 83. Let f and g be continuous, and then they're giving the values of integrals. So we're going to, you know what we're going to do. We're going to use the properties of integrals to solve this out. So they want to know what this integral would be. So it looks like we're going to need to figure out this and then subtract 3 times the same bounds on g. Does that make sense? Now 0 to 3 on g, let's start there. They gave us 3 to 0. So what does this equal? This would be positive 7. Because the bounds are reversed, you just change it to positive. Now let's back up. 0 to 3. Well, this is 0 to 6. This is 3 to 6. So wouldn't 0 to 3 be the whole thing minus the part? Gives you the other part. So this would be 9. That's the whole thing. Minus the other part gives you the 0 to 3 part. And we also need the half out front. Notice I haven't used a calculator at all. In fact, I still don't need it because 1/2 times 4 is just 2. Minus 21 is -19. And -19 is the answer. See how easy that one was? That was, whenever you get to a question, it's not a bad idea to take a half of a second and think, what is being tested here? This was just properties of limits and how you can manipulate those bounds. All right. 84. 84, here we go. The regions A, B, and C are defined here, and the areas are 14, 16. Now notice that's under the x-axis, so I'm thinking, oh, that's going to be negative. And then C is 50, 50. What is the average value of f on the interval 0 to 8? Now, average value is where you take the integral on the function, not the absolute value of the function, just the function, and you divide by b minus a. So this would be 1 over 8 minus 0, of course, right? What about the value of the integral? All we have to do is add up the areas, but don't forget the 16 is negative. So it would be 14 plus negative 16 plus 50. So that's 1 over 8 times. You can do that in your head without a calculator. Do it. I bet you'll do it more quickly. 48. And look at that. 48 divided by 8 is 6. And that is the correct answer there on 84 is A. We haven't used the calculator this entire video. Now in this next one, I believe we do. And you can see the answers are decimals. So let me bring the calculator back for you. There it is. So we got it all queued up and ready to go. A particle moves along an x-axis, left and right, possibly, according to this velocity function. So don't forget, it could go left and right, right? What is the total distance traveled? So sometimes velocity could be positive, sometimes it could be negative. So we don't want to just integrate on the velocity function. That's called displacement. What I've got written there would be displacement. What do I have to do to get total distance? I have to flip the entire graph up over the x-axis so it's always positive all the time, and then I can add up all those rectangles, right? That's what integrals do. Those Riemann sums that you spent so long doing. All right, so we go to the calculator on this. Math, number 9. The integration from 0 to 2. Oops, 0 to 2. And the function is a fraction. Now, I do need to do the absolute value. Now, that's under math. And you go over to num. And number 1 there is ABS. Right? And then I'm going to put a fraction in here. So I do have to put the top inside parentheses. Oops, and it didn't work, did it? Yeah, it did. Okay. X squared minus 1. Now I'm going to close my parentheses and divide by, I have to open another parenthesis, x squared plus 1. X squared plus 1. I close my parenthesis. I change this to a dx problem. And I think I'm ready to hit go on this. And let's see what the answer is. 0.927. All right, and I'm looking at the key, and what do you know? We got it right. All right, so that was a calculator question. The absolute value was really important there because of the magic word total distance traveled. We needed to flip the entire graph up above the x-axis. All right, let's do these two, and then that'll be the end of this video, and then I'll finish it out on the next video, which will be linked in the playlist. Line L is tangent to the graph of e to the x. Okay, so you know what e to the x looks like, right? It looks like this. This is y equals e to the x. So we're at k, we are at e to the k, wherever the heck that point is. All right, you with me so far? What is the positive value of k for which the y-intercept of the tangent line is 1/2? Well, what I'm starting to think about here is y equals mx plus b. And since it goes through 1/2, I know the y-intercept is 1/2, right, on the y-axis. Now, how do we get slope of a tangent? That's just the derivative. And y prime would be also e to the x. So y prime at k, the slope at k is what? E to the k. All right, so what do we have so far? We have y equals e to the k x plus 1/2. Now the point, remember the point was k e to the k. That's your x and y that we're going to go ahead and plug in. So let me zoom in a little bit here for you so you can see better. So this would be e to the k over there equals e to the k times k plus 1/2. Now, personally, I would do just a pinch of algebra at this point, but you could go to your calculator and type this in as y1, and this is y2, and find where they hit, where they equal. But before I do that, I'm just going to change it a little bit because I think it might save me a little more time. So e to the k minus e to the k times k equals 1/2. I then factor out an e to the k, and I get 1 minus k equals 1/2. You know, at some point you may be holding out, I know when I was previewing this problem earlier, I was holding out hope that I might be able to solve for k, but you cannot here. E to the k equals 1 over 2 to the quantity 1 minus k. At least you can't easily solve for it, I guess I should say. So I want to put these into the calculator. All right, so we're going to go to our graph. I haven't done any graphing yet in this, so I'm going to type e to the x. This problem takes a little longer simply because of all the data entry here. 1 divided by the quantity 2 times, I'm going to do another quantity, 1 minus k, but I have to use x, of course. All right, and then graph it. Let's see what we've got. All right, so there's my e to the x. Here comes my other one, and you can see there it does hit it. So let me just zoom in here a pinch. I'll hit enter. Let's redraw it. All right, so I would really love to find this point right here. Wouldn't that be great? So how do we do that? We do use the intersect feature. Okay, so we do secant, calculate, which is above the trace button. You guys probably know all this, but I'm just trying to talk you through it. 5 is the intersect feature, and then it says, okay, I need to know the two functions. So the first function is the blue one, second one is the red one, and now I'm going to scroll. Oops. I'm now going to scroll. Let me clear this out. Let me try this again. Second, calculate. 5. Enter, enter. And I was hitting the wrong button for scrolling. So I'm going to get myself a little closer because it actually hits twice. So you do have to get closer to this one than the other one. I'm now going to hit enter. And I see the intersection happens at x equals 0.768. 0.768. And number 86 is indeed 0.768. So there you go. That was the answer there. So hopefully you followed all that. Again, we could have put it in at this point. Probably wouldn't have been any harder, honestly. But I just decided to do it that way because I'm an algebra teacher, so I like to do a little bit of algebra because I think I was holding out hope that I could solve for k and actually get an expression rather than doing this graphically. But I think graphically was the way to go. All right, moving on. A differentiable function f, so that means the derivative exists everywhere. There's no corners or cusps or crazy things happening on this thing, has the property that the slopes are always under or equal to 3. That's what, when I'm thinking about this, I'm thinking the rate of change or the slopes are all under, let me write that down. The slopes are all under 3 between 1 and 8. Okay, so let's do 1 here and 8 over here. Now f of 5, which would be right here, is 6. That's a given. Which of the following could be true? Now remember, this thing has slopes that are up 3 over 1 at the most. Let me say that again. Slopes on this 3, the slopes on this function are always 3 or less. It can't be steeper than up 3 over 1 at any point in time. Hopefully that makes sense. So, could we possibly start f of 2, could that be 0? I'm sorry, at 2, could we start here? Well, sure, if we go up 3 over 1, up 3 over 1, I'm well above that, so I could certainly go at a lower rate than 3 and get there. So, yes, that one's possible. All right, let me get this mess out of the way. Now, if f of 6 is 2, is that possible? That's an easy one because the slopes are allowed to be negative. This does not say the slopes are always positive. So yes, we could be here and then we could go down here with a negative slope. So that one's possible also. All right, so what about f of 7 being 13? Way the heck up here at 13. F of 7. Could that be 13? Well, if we start here at 6 and we go up 3 over 1, we're now at 6, 9. And then if we go up 3, which again is the maximum rate that we can do, and then that would put us at 9, and then we would be at 12, right? We went up 3, I'm sorry, this is at 7. Up 3 over 1. So could we ever have gotten to this point up top? Nope, because this was the fastest rate we could have ever gone. And that last point is above that. So the answer is 1 and 2 only. So this was a problem testing your understanding that first derivative represents slopes. So your curve can slope at a max of up 3 over 1. That's the best you can do at any given point. So that last one, Roman numeral 3, was above the trajectory. That was our maximum. All right, I'll continue with number 88 all the way to the end on the next video. All right, hopefully this is helping you. All right, we're making progress through this calculator section of the 2004 released exam. Let's start with number 88. The graph of a differentiable function is shown above. So that's the original function f. Let h be a new function. And h is defined as the integral of what we're looking at. Which of the following correctly orders things? So the function, this would be the integral of 0 to 2 on what we're looking at. Well, that's just the area. Okay, they want us to put them in order, by the way, from biggest to smallest. So I'm seeing that this one's actually a pretty big positive, right? That's all above the x-axis. So let's keep going. I see that the function f crosses through the x-axis there and changes to be negative. So the derivative of an integral is just the function. Okay, so let me write that down. H of 2 is actually just what we're looking at here. H prime, I think I said it wrong, H prime of 2 would just be the derivative of an integral with x plugged in, so that would be f of x. So this would be 0. And that's because I'm looking at the point 2, 0. I'm just looking at it. I'm just reading it off the graph. I'm not looking at slopes at all. I'm just reading it off the graph. And then they want us to talk about second derivative. Now the second derivative would be the derivative on what we're looking at. So the second derivative would be slopes. So as I'm looking here, I see that the slope is negative. That's all I need to know to put these in order, folks. H of 2 is definitely the biggest. H prime is in the middle. And then H double prime is the smallest. And that was option E here on the answer set. All right, so all you had to do was analyze positive and negative. Of course, the fact that the derivative of an integral is just the function was part of the test here. And I think just reading that point off the graph might be tricky for students also to recognize that what they're looking at is actually h prime. So they can just read it off the graph what f prime would be. All right, moving on. 89. What is the area enclosed by these three things? All right, so if you go to the calculator and we're going to do that here in a second. E to the x, of course, minus 2 would be down here, and it would be going up like that. That would be e to the x minus 2. And then the sine function is going to start here and go up, and it's going to hit at some point. You could, take time to reason it out, but where it might hit, but we're going to use the calculator to do that, of course. And then x equals 0. X equals 0 is just a vertical line right there. So we need to figure out this value right here. I'm going to call it a. So we need to integrate from 0 to a on the upper minus the lower, right? I'm sure your teacher drilled that into you. So the upper function here clearly is sine x minus the lower function. And because it's e to the x minus 2, you have to put it in parentheses when you put that in the calculator. Otherwise, you very well could get this wrong. dx. All right, so there's the integral we need to plug in. All right, so we will need to figure out where they hit. We could try to do that algebraically, but I think in the end it's going to be faster to just do this with a calculator. So there's my calculator. I'm going to go to y equals, and I'm going to type in e to the x minus 2 for my y1. And then, and by the way, I'm going to show you a really cool trick that maybe some teachers don't show their students. So make sure you're paying close attention to what I do here. I'm going to show you two different tricks. All right, so if we go to graph this, I might need to reset my window because it's left over from before. All right, so let me go to window. Well, actually, we're okay. We're okay. So you can see it hits right here. So that's the value that we're going to need to find. There's that vertical line that I talked about. So we're going to be integrating from here to a, whatever the heck a is. And don't assume it's 1, because I don't think it is. So we do second trace. That gets to calculate. You go down to intersect. And it says, okay, tell me what the two functions are. 1, 2, and then you got to navigate, somewhat close to where it hits. Hit enter. And there it is. The intersection is this number right here. Now, I'm not going to write that down. I guess I could, but just because I don't like, especially on when you get to the free response, you do not want to be using rounded numbers to do any other calculation. So right now, x equals this. So here's the first little trick I'm going to show you with the TI. Currently, the variable x now holds that number. So if I type x, it's that. But I could lose that. Like if I trace somewhere else on the graph, I'm going to lose that. So watch what I do. I'm going to store it. So what you do is you take the value and you hit that STO button with the arrow. I like to think about it like you're shooting the number into, I'm going to store it in A. So now let me hit enter and it says, okay, yeah, I did that. So watch. Now whenever I type A, it has that number stored. Now I'm going to just use A when I type it in. Watch. I'm now going to go to math, integration, which is number 9. My bounds are going to be 0 to A. All right, here's the second trick. So the first trick, you guys probably knew how to store variables. Rather than typing sine x, do you remember that was my y2, wasn't it? So you can click the vars button, vars, V-A-R-S, go over here to the y variables, select function, and select y2. Boom. So that's actually sine x minus, I'm going to do y1. So I'm going to go back to vars. I'm going to click to the right to get to my y variables. My function is y1. So that's the upper minus the lower. Upper minus the lower. And I'm going to put an x here because that's my variable. So I didn't have to retype things. I think that's probably quicker than retyping, and time is of the essence, as you know. So let me hit enter, and I get 0.745, and that is C. And I'm looking at the key, 89. C is the right answer. What do you know? We did it. All right, moving on to number 90. A particle moves along a line so that its velocity is given by this. Now, this is a cubic, and with also, oh my goodness, with an exponential at the end. So some crazy stuff is going on here. This thing could be positive or negative. Do I care what it looks like? Not yet. I'm not sure that I'm going to need to know what it looks like, but let's see. For what values of t is the speed of the particle increasing? Okay, so speed is the absolute value of this function right here. So when is it increasing? So that would be slopes are positive on the absolute value when we're moving away from the x-axis on the absolute value function. So I think I do actually want to graph this. So let's go back to y equals. I'm going to clear out these two. When typing this in, don't forget to use your absolute value. So we're going to do the absolute value of the given function. Now take your time plugging this in, minus x to the third. Real easy to make a mistake on your data entry. Plus 2x plus 2 raised to the. So up in the exponent is your variable like that. Now make sure you got that absolute value. All right, double check, look at it again just to make sure you typed it in right. And I messed something up, didn't I? I forgot the square, so I'm glad I looked at that. Second insert, I am going to square that. There it is. Plus 2 to the negative x. And now I hit my graph button, and let's look and see what this graph looks like. All right, it's coming down, of course. Oh, then it goes back up, then it comes down, and then it goes up again. Now remember, this is velocity, and we want to know when is the speed increasing? When is the speed increasing? So speed would mean, when is this increasing? It means when you have positive slopes. When is it moving away from the x-axis? So this is from here to here, it's moving away. But then the speed actually goes down for a bit, and then, boom, something happens here, and the speed starts going up again. All right, so the answer is whatever this number is to here, union from here and beyond. So you can look at this and pretty well know the answer, right? Because this is 1, this is 2. So it's got to be this one down here. Here's my 2 to infinity. And then these numbers right here, if you were to trace this function, I'll show you. If you trace this, there's your 1.7 or 0.17, this number right here to start out with. And then it does peak at 1.2. So you can be pretty confident without doing a whole bunch of wasting of time that option E is the correct answer, and that is the correct answer. All right, moving on. I think we have a couple more here. Let f be a function defined by all these tables. So I can't quite get them all on the screen for you, but we'll be able to find the answer easy enough. Let f be a function defined such that it's always increasing. This means f is increasing all the time. That's what you need to write down. And it's concave up. What does that mean? That means it's accelerating. So this is concave up. So I'm starting to think like an exponential or something. You see how I reasoned all that out with just those 2 bits of information. So going through, which of these appears to be accelerating up? This one goes down by 1, down by 2. Oh, that's accelerating in the wrong direction, actually. So it's not A. This one, as these go up by 1 every time, these are accelerating. So B is a possible answer. Let's check the others just in case. These are just going up by 3 every time. That's linear. That's not the answer. Letter D. This goes up by 8. Then only by, what are we going up? 6. And then up by 2. Well, that's actually decelerating. That was actually concave down, I think. And then this one is down 1 and then up. This is all over the place. So that's not it either. So the only one that it could be is letter B, and that is the right answer. All right, number 92. 92. I think this might be the last one, and it is. So here we go. You ready? This is a good one. I like this one when I previewed this one earlier. A table gives values of the differentiable function. Let me get rid of my calculator here. I don't know that we're going to need it anymore. It might be a distraction. Functions f and g are above, and also, of course, the derivative just on f. But we don't have a g prime column. We don't have a g prime column. G, as it turns out, is the inverse of f. So what is the value, what is the slope of the tangent line at 4 on G? So back in pre-calculus, you learned that if this point is on, okay, if f of A is B, right, then over here, on the inverse, a B is going to turn back into an A. So let me give you some numbers to make this more real. So if this were 5 and this were 1, then this would be a 1 and this would be a 5. So on f of 5 turns into a 1. On the inverse, then a 1 turns back into a 5. Do you remember what's true about the slopes? So let's say this is f. What does the inverse look like? The inverse is symmetric across a 45. So if the slope here, I'm just going to make up numbers, okay? So if the slope here is up 2 over 3, then over here it's going to be reversed. It's going to be up 3 over 2. It's the reciprocal. So we're going to need all that information in this problem. They want us to figure out g prime at 4. So I go down here to 4, and I see on G, 4 turns into -2. That's on G. Now remember, G is the inverse. So the sister point would be up here, where a 2 turns into a -7. You with me? And then the slope there is up 4 over 1. So therefore, the slope on the inverse of function would be what? The reciprocal. It's 1/4. It's 1/4. The answer there is 1/4. So that was a lot of processing and really understanding what goes on graphically in these values. It's a pretty neat question. I remember trying to write these questions to give tests to my students, and it was always a challenge to write them. So this is a pretty cool one. All right, so hopefully this series with the calculator section has been helpful. I will definitely do the free response problems on this 2014 exam also, and I'll include that on the playlist. All right, good luck in all your studies. All right, so you've tackled the multiple choice questions, both no calculator, calculator, hopefully. Now we're going to go on to the free response, the dreaded FRQ questions. We've got 2 questions. We're allowed to use the calculator on these. We won't need it for everything, of course. And we're going to try to get through it as quickly as we can. Okay, so this first question, it says that Ruth rode her bicycle on the trail and she recorded her velocity. And here's all the information in the table. Now, as I look at the table, the first thing I noticed was that these are all 0.4. And you should be very happy about that. That means we have nicely even intervals. So we can do Riemann sums and stuff if they want us to do that. So that's going to be helpful. All right, for selected values over the first 2.4 hours, as shown in the table. Okay, and also, do you notice here it says the velocity is always positive? So that's nice. That means there wasn't any major crazy turning around or something, I guess. Use the data in the table to approximate Ruth's acceleration at 1.4 seconds. Now, 1.4 seconds is right in between here, right? And acceleration, as you know, acceleration is the derivative of velocity. Now, the best we can do is just find the slope of the secant line here. Find the slope of the secant line. So we would say the acceleration is going to be the velocity at 1.4, and then we really should put an approximate symbol there because it's roughly equal to, we would take 16.3 minus 17.2 all divided by 1.6 minus 1.2. And you know, one thing you could have done here also was to do the velocity at 1.6 minus the velocity at 1.2 all over 1.6 minus 1.2. If you want to insert that in there. I don't know that that would be required, but all right, equals negative 0.9 all over 0.4. That's negative 2.25, and this would be, what is the unit here? This is important, the unit. This would be hours per, it would be miles per hour squared. So always take your time on that. Remember, like we often see like meters per second squared. So a distance per time squared. All right, so let's continue on to number 2. I think we answered everything in there, right? We indicated our units of measure. We did that. And we showed our calculations. So I think we'd get full credit on that. We can certainly check it against the rubric. Using correct units, interpret this. The integral from 0 to 4 on that velocity function in the context of the problem. All right, so since v is always positive, I would put that, I don't know that it's recorded, this would be the same as the absolute value. So this is the total distance traveled. Traveled in miles for the first 2.4 hours. Okay, and then part 2 here says use a midpoint Riemann sum with 3 subintervals of equal length and values from the table. So 3. Well, conveniently, we've got 7 points. So since we have 7 points, we have one rectangle here. Sorry, we have one midpoint here. We can use that as one of them. And then we'll be able to do a midpoint here between that. And then we'll be able to do a third midpoint here. Okay, so the midpoint values are this, this, and this. All right, and remember it was a width on each one of 0.4, so the total width on each of these 3 rectangles would be 0.8. And 0.8 times 3 is 2.4. That gives you the entire 2.4 seconds. All right, so let's get this down. This would be, so it says integral of 0 to 2.4 vt would be, dt, would be approximately equal to 0.8. That's the width of all 3 of the rectangles, right? They're all 0.8 width. And then we just need to do 11.8, 17.2, and what was that third one? That third one was right here, the 16.8. 16.8. All right, and we run that through our calculator. All you have to do is type this in, and let's see, you get 36.64. All right, what would the units be on this? 36.64. right? This is total distance traveled. So don't forget your units. This would be miles. All right, moving on, letter C. For those first 2.4 hours, Ruth's velocity can be modeled by this function here. All right, so that's the velocity function. So g of t is velocity. We finally have a function instead of working off the tables. According to the model, what was Ruth's average velocity during that time period? Well, how do you do average velocity? Whenever you're finding the average of anything, don't you add up and divide by how many there are? Yeah. So that's how I remember this formula. So the average velocity equals, you add up all the velocities, and we don't have to rewrite it. Don't waste time rewriting it, folks. GT, and that is going from 0 to 2.4, right? And then you have to divide by how many there are. So that is the b minus a part. So it ends up being 2.4. Now, I would like to show you a trick that in the calculator right now that may come in handy. In fact, I think it will. So we're going to come over here to the calculator and actually type in this in under y1. And I know you're wondering, why the heck is he doing this? Do we really care about the graph? And the answer is no, we don't care about the graph. But this might save us some time. In fact, I'm pretty sure it will. So let's see, I want a 6x there. And then I'm going to divide by x plus 0.7. Close that. And I'm just going to make sure I typed it in right. 24x plus... All right, that all looks pretty good. So now I can quit out of here. And so what does that do for me? Well, if I never have to type that in again, I've got it stored under the y variable. Now we're going to use finite integration. So we come in here and choose number 9. And I'm going to integrate from 0 to 2.4. So 0 to 2.4. And then on the inside, I'm not going to retype the whole function because I've already typed it in and I've stored it. It's recorded in the y1 variable. So if you hit the vars button on your TI calculator, you can go over to y variables and then choose function and choose number 1. And there it is. And dx is our variable. Now don't forget, we are going to need to divide this. If you look at my whiteboard there, we have 1 over in the front. I'm going to insert 1 over 2.4. So don't forget to divide by 2.4 after you get your answer. So we hit enter and we get 14.06, make sure you round correctly, 14.064, and then of course the units here are miles per hour because this was the average velocity. Now we have that stored in y1, so we may end up using that again on part D because I think we've answered everything on this screen now. So according to the model given in part C, Ruth's speed increasing or decreasing at time t equals 1.3. Now 1.3 isn't in that table, so we have to use that function to figure out, first of all, what is the velocity at 1.3. Now the good news is I've stored it in y1. Let me remind you, here it is. It's in y1. Now I have to set x to that number though. So here's how you do that. You do 1.3 and then you use that STO with the little arrow. I think about it as like shooting the number into the variable here. We're going to shoot the number 1.3 into the variable x, and it'll say, okay, I did that. Now I'm going to use the y variable. I'm going to select vars, y variable function, number 1, and basically it's going to execute that and run 1.3 through that function. I didn't have to type it in again. It sure saved a lot of time. So this is 18.096. All right, and this would be miles per hour. And since acceleration is the same thing as the derivative on our function, I'm going to use my numerical derivative feature on the calculator to do that. So I go to Math. I'm going to go down here to numerical derivative, number 8. And I hit Enter. There it is. We're going to hit dx. All right, so again, y variable. I don't have to type it in again. I hope you are in absolute awe at how awesome this is and how much time this can save you if you utilize it. And then, where are we evaluating at? 1.3. So we don't have to shoot any value into x. It does it for us here. So we get 3.761. This would be miles per hour squared. All right, so we have to reason this out. So speed is the absolute value, right? It doesn't matter about sign. So you're speeding up if you're going to the right and acceleration is also going to the right, or if you're going to the left and acceleration is also going to the left. Since these are the same sign, so Ruth's speed is increasing at t equals 1.3 since v of 1.3 equals 18.096, which is greater than 0, and the acceleration at 1.3 is 3.761, which is also greater than 0. Speeding up since velocity and acceleration have the same sign. All right, so it's important to say that you recognize that velocity and acceleration need to have the same sign, maybe at t equals 1.3. All right, so that's question 1. Hopefully you feel like you got something out of that. You can check the rubric, which is posted online. I've got it over here, and I think we did everything that we needed to do. All right, so let's go on to the next one. We'll go ahead and just push forward to the second question on the calculator section. A store is having a 12-hour sale, and the total number of shoppers that have entered the store after the sale begins is modeled by the function that you see here. So people are going in the store. This tells you how many people have entered the store. Total. At the time t equals 0, when the sale begins, there are no shoppers in the store. All right. At what rate, when I hear that, I think derivative. Well, what rate are the shoppers entering the store 3 hours into the sale? So I think we need to find the derivative of this thing. And then after we do that, we're going to plug 3 into that and see what we get. So the derivative here is 2t to the third minus 48t squared plus 288t. And we're going to plug 3 in. So that would be 2 times 27 minus 48 times 9 plus 288 times 3. And you add all that up, and you get 486 shoppers. Now, it's not total shoppers. Remember, this is the rate. Shoppers per hour. So make sure you get that unit right, because otherwise they're going to dock you a point on the rubric. All right, so I think we answered everything on number 2A. So let's go down here. Find the value of 1/3, and got an integral there, of the rate function using correct units and explain the meaning of that thing. So the integral of the derivative is just the original function. So this is 1/3 times s of 9 minus s of 6. So this might be where, you know what, maybe we need to go back and put it in the calculator so that we can save a little time here. I don't know. So let's see, let's just do that. Let's clear this one out. 0.5 x to the 4th minus 16 x to the 3rd plus 144 x squared. Now I want to make sure I got that typed in right before I go back down. That looks good. So I can do second quit. And now what I'm going to do is I'm going to shoot the 9 into the x variable. That way it's stored in there. Okay? And then, now that I have 9 stored in there, I can hit vars, go in here to my y function, and that is going to give me what s of 9 is. So this would be 1/3 times the quantity, 3280. So I'm hoping that time that I put in up front will save the day. So now I'm going to run 6 into x, and then just do the same thing again. I can come up here and just hit enter, I believe, and save some time. 2376. And you can now type that in your calculator, and you should get 301.5. All right, so we found the value of it. Using correct units, explain 1/3, the integral 6/9 on this rate function is the average rate that shoppers are entering in shoppers per hour. So if you want to put shoppers per hour up here, that should do it. So is the average rate that shoppers are entering the store in shoppers per hour. Okay, so I'm just checking my work to make sure I got everything, and it looks like we did. We got it. That's all we have to do there. All right, so letter C. The rate at which the shoppers leave the store is given by the rate, that's the rate function, is measured in shoppers per hour, is modeled by this function here. That's a rate function. According to the model, how many shoppers are in the store at the end of the sale time? Well, shoppers are going in according to s of t. So we're going to have this new function. I could call it f of t, or the number or something. It's going to be the number that have entered minus the total that have exited. Now remember, L is actually a rate function. So it would be the integral from 0 to t on -80. Well, let's save time and just write L of t dt. All right, so according to the model, how many shoppers are in the store at the end of the sale? So we would have to do s of 12 minus the integral from 0 to 12 on L of t dt. On L of t dt. So we already have S. We already have S in there. So let's just go ahead and utilize that. We're going to, what do we do? Number 12. So we're going to shoot 12 into X. I'm going to hit enter. And now I'm going to go back up to that Y variable again and hit enter, run it again. So this is 3456 have entered during the entire course of that 12 hours. And now we're going to see how many people have left. Now, we have that ugly function up there as well. And we might need to use it in part D again. Right? So I'm wondering if we shouldn't put it in on Y2. So let's just go ahead and do that just in case. All right, so this is going to be negative 80 plus 4,400 divided by the quantity, x squared, minus 14x plus 55. Just checking my work before I go on. See, so that didn't take that long, right? So now we do second quit, and we're going to go to math. We're going to finite integration this thing, 0 to 12. But this time we're going to use y2. So I'm going to go over here to my y variables, and I'm going to hit number 2 to get y2. And this is dx. All right, let's see what we get. We get 3260.298316. And then I'm just going to subtract my 3456. Hit enter. Of course, don't worry about the sign. This is negative 195. Well, I said don't worry about the sign, and then I wrote it, right? It's 195.702. There are approximately 196 shoppers in the store at t equals 12 hours. All right, so this, we've got our units here, shoppers, and we went ahead and rounded it to the nearest whole number, just like they said. Make sure you follow the directions. All right, I think we answered everything there, and the good news is we have both functions stored now in our calculator for part D, just in case we need it. Using the given models, I think they may come in handy. Find the time at which the number of shoppers is the biggest. Ooh, that sounds like a maximizing problem, doesn't it? So you remember how we do maximizing? We find the derivative, and we set it equal to 0. And that's a horizontal tangent, and then we hope that that's a maximum. Now we'll need to check that we're underneath on both sides, but that's how we're going to do it. So let me erase that. We don't need all that there, right, to gum up our answer. Using the given models, find the time. So we're going to find the derivative of this thing up here, which would be, so the number at any given time was this minus this. All right, would you agree? That's the total number at any given time that are left in the building. We want to maximize this. So we're going to take the derivative, which would be s prime of t minus, now the derivative of this is just L of t. And we set that equal to 0, and we solve it. Now, so we had the derivative function earlier. The derivative function is right here. 2t to the third minus 48t squared. 2t to the third minus 48t squared plus 288t plus 288t minus your L of t, which was up above. So we got to figure out where that hits the x-axis. I think let's do it numeric, or let's do that graphically. So we're going to come in here, and let's see if I can do this. I think I can. 2t, 2x to the third. I'm typing in the derivative, minus 48x squared plus 288x. All right, just double check that I typed that right. Minus 48x squared plus 288x minus. All right, so I'm just going to put, I'm pretty sure I can do this. I'm going to put that y1 in there. I'm going to go to vars. Y2 is going to go in there. Okay. All right, and then I'm going to come over here, and I'm going to turn these graphs off so that they don't distract us. All right, let's see if we can graph this. All right, so it does look like it hits the x-axis somewhere in here, right? So this is the time. So we had to be looking between 0 and 12. 0 and 12. So I've got 0 and 10 here, so I guess we lucked out. So we want to find the x-intercept. So we go to second trace, which is calculate. We're going to calculate a 0. And the function we want, right, it's asking us, or it's asking us for the left bound. I'm going to actually come over here. See if I can get closer. You're supposed to go a little to the left. All right, so I'm not seeing it there. All right, so let's just do this. We'll go from 1, enter. And then we're going to go all the way over to something like 9, enter. There it is. Now it's showing it to us. So we want a 0 in that region. And sure, the guess can just be that. And we hit enter. 0 is at 5.5450066. All right, so now I'm going to, now x has that number in it. Don't forget, x has that number in it, so that we're going to use that to our advantage. I'm now going to come in here and type variables, and you know what I'm going to use? I'm going to use my y3 this time. I'm going to have it execute that, and that confirms that at t equals 5.5 seconds, the derivative is 0 there. So the rate of change is 0. All right, so we do need to figure out how many were in at the beginning. So let's do 0. Well, we know there was 0 in the beginning, right? So we can do a little table here. We can call this n, right? So at the beginning, there is 0. After 5.545, we have to find n of t. We have to find n of t. So we're going to actually have to do some crazy stuff here. So here we go. X still holds that, right? X, let me just double check. It should still hold that 5.5. So we'll go into the y variables. We're going to take our original function, number 1, and we're going to, so I'm doing this up here. I'm doing this right up here. I'm going to subtract. And let's see, I have to do math. Finite integration from 0 to, and we're going to do to x. Okay. We do 0 to x. And that is going to be, actually, let's put the 5.545 in there just to not mess things up. And then, do you remember that y2 holds the other thing here? So we go over to y2. 1, 2. Oops, what did we just do? Variable 1 and then 2. There it is. Dx. All right, this should be how many people are in the building after 5.545. This is 1361.863. All right. And then at t equals 12, let's see what's happening at the end. All right, so I just back this up. Well, I do need to do something else. Do you remember what I have to do? Not only do I put the 12 there, I'm going to save some time. I'm going to go ahead and hit enter, but that's not going to be our answer. We still have to store 12 in x so that y1 will work. So now I can come up here and I can hit this. And I get 195.701. So since this is higher than both the endpoints there, we could say, so there is a maximum number of shoppers after t equals 5.545 hours. All right. Since 0 is less than 1361 and 0 is less than, and 195 is also less than 1361. All right, so the justification on the rubric is really they're using this table to show that, and then you just have to really spell it out what your answer is, and make sure you have your units there in the end. That's really important. So the important thing in the rubric, it says that that you wrote that somewhere, and that you were analyzing that for where it hits 0. All right, we'll go on to the no calculator section next. So hopefully this is helpful. I've enjoyed going through this exam for you. All right, we'll see you next time. All right, let's continue our adventure on the 2014 released AP Calculus AB exam. This is the last section. It's 4 free response problems where you cannot use your calculator. Now I'm just going to go through the first 2 in this video, and then I'll put together a video with a separate video of those last 2 problems. So let's dig in. Looks like you've got 60 minutes for these 4 problems. If you have extra time, you are allowed to go back to the previous section, just you don't have your calculator anymore. So that's one strategy that some students do take advantage of. So this is no calculators. All right, let's look at number 3 here. It says e to the 2x, so f of x equals e to the 2x. That's what we're looking at here. Let R be the region in there. Sounds like we're going to be doing an area, maybe revolving kind of problem, right? First quadrant bounded by the graph that you see there. and the vertical line x equals 1. Notice they gave you this point up here. When 1 goes in, e squared comes out on that function, of course. Write an equation for the line tangent of the graph of f at 1. So looking for this right here. I'm sorry, at x equals 1, that would be up here, of course, at x equals 1, not y equals 1. All right, so we have a point, and that's 1 e squared. So what else do we need? And then we'll have it. We need the slope. We need the slope. Remember that equation, y minus y1 equals m times the quantity x minus x1? All we need is the slope, and we'll be in good shape. So where does the slope come from? The derivative. So the derivative on f of x would be 2 because of the chain, right? Because of the chain, you know that, right? And then you plug 1 in there. F prime of 1 equals 2e squared. So we're ready to write the equation of the line. Y minus e squared equals 2e squared x minus 1. And you can just leave that answer like that, or you can add e squared to the other side if you'd like, and you could do that. All right, so that's the line tangent. Find the area of region R. Well, you want to think about which way do you want to run your rectangles. Are these going to go vertically or horizontally? You can do it both ways, but there's an easier way here, and that is vertically. If you run vertically, you don't have to worry about any sort of subtraction or anything. So we've got the integral from 0 to 1 because we're doing this with dx's as our width on our rectangles, right? So it's always upper function minus lower function, but we only have one upper function. It's that y equals e to the 2x function. So we're going to integrate from 0 to 1 on e to the 2x there, dx. So the area of the region is the integral 0 to 1 e to the 2x. So u would be 2x, du equals 2 dx. So dx is 1/2 du. So this would be the integral of e to the u du, but we're going to have a 1/2 on the outside. And then let's go ahead and change the bounds because it'll make our life easier here. If you plug 0 in here, you get 0. If you plug 1 in, you get 2 out. So now you do the antiderivative, and of course the antiderivative is just e to the u. You evaluate it from 0 to 2, and you get 1/2 times the quantity e squared, but don't forget, e to the 0 is 1. So you would have minus 1 there. E squared minus 1 in parentheses, all times 1/2. That would be the area of that region. All right, moving right along. Letter C here. The region R forms a base, and then up from the base is going some cross section. So this is not a revolution problem. This is not rotating around one axis or the other. We are going to be having squares that go straight up from, it says perpendicular to the y-axis. So I always like to try my best to draw these somewhat with perspective here, maybe to give students some help understanding this. So this is sort of shooting up like that, and down here we have another square kind of like that. All right, so these are squares that are going up in a three-dimensional way. So how do you find the area of a square? It's just side squared, side times side. So if we could figure out this side, then we just square it. That would give us the area. And then, of course, we integrate it over the entire thing. But I want you to notice that in this region right here, we actually just have a box. From 0 to 1 on the y-axis, we just have a box. So we want to keep that in mind. That's 1 by 1 by 1. So this volume of that box is 1. So if you're following me here, we're really just needing to use calculus on this region higher than that. Now, since this is going to be a dy problem, right? Our squares are running left or right. This is a dy problem. We have to solve for x up there in the original equation. So the original equation was y equals e to the 2x. So how do you solve for y? Well, you do the natural log on both sides. You get the natural log of y equals 2x. You then divide by 2 or multiply by a half. So x is the same thing as 1/2 natural log of y. So we've solved for x. That means we now know, let me change colors here, it might help you out. We know the distance from here to here at any given moment, right? But in order to get the distance from here to here, we would have to subtract 1 minus. So, by the way, in the problem, I didn't read it, it says, but do not evaluate. So that's kind of nice. So we can go ahead and set up our integral. Our integral is going to run from 1, remember they're y numbers, all the way up to e squared. And I just said a moment ago that the width of every single square is actually 1 minus our function up above, which is 1/2 ln y. And then we're going to square that. All right, the volume equals, but do not forget there was this box on the bottom. So we're going to have a 1 plus on the bottom there, and don't forget our dy. And we have our answer, and I'm just checking, and I've got it exactly like they do in the rubric. You've got to have the bounds correctly set up, as well as the integrand in there, and of course the 1 plus out front to get all 4 points on that thing it says. All right. Let's move on to number 4, which is the second problem here in the no calculator section. The continuous function is given above. Now notice that it has some corners. You should really take note of that. The graph of f is given here, consists of 4 line segments. Let g be the function given by this here. So it's got this portion right here. So what is this? This is the area under the curve from -2 to wherever. That's what this represents. And if you go backwards, it'll be negative. And I think they actually try to trick us on that here in a moment. All right, so the first thing is g of 0, to find g of 0. So if you plug, so g of x, g of 0 would be 2 times 0 plus the integral from -2 to 0 on the graph that we look above. So you remember when you first started learning about integrals, you used areas to solve them, and that's what you have to do from here. We're going to go right in here. We have to find that area right there. So that is a trapezoid. So trapezoids, you do base 1 plus base 2, and that's 2, right? This is 1 high, this is 2 high there. All divided by 2 times the height of this thing, which is 2. So that's the way I would do it personally. These 2's cancel, and you end up with 3 as your answer for g of 0. Now g of -5, I'm going to erase that because now we got to do g of -5. G of -5 is over here. But notice we're going backwards this time. So g of -5 would be 2 times -5, that's -10, plus the integral from -2 to -5 f of t. Now, if you want to reverse those bounds, you have to change it to a minus sign. So it wouldn't be a bad idea to actually do that, because usually we like to see the smaller number on that lower bound. So you could do that there. So we have -10. All right, we have to find the area of this. All right, so how tall is that? That is 4 by 2. So that's got an area of 4. But remember, it's under the x-axis, so it would actually be -4. And then this is above the x-axis, and it is a base 2, or I'm sorry, base 1 with a height of 2. So that's a volume of 1, or an area of 1. So we would add 1. So that ends up being negative 3 in there. So negative 10 plus 3 is negative 7. And both of these are the correct answer. So you want to show all your work there. All right, moving on. Find the derivative in terms of f. So let's do that first. G prime, I've got it written down here for you again. G prime of x would be 2 plus, now remember the derivative of an integral is just the original function with the upper bound plugged in, and then sometimes you had to add on a chain, or multiply by a chain, but we don't have a chain here. So that is the problem right there. So then they ask us to find the second derivative. So the second derivative, I would just go ahead and write it, is 0 plus f prime. Oh, how do you find f prime? That is just slope on this graph. So we're going to read the slopes off. That's all we're going to do. So for example, g double prime at, the first one is what, 4? Yeah, so we go to 4. 1, 2, 3, 4 right here. And we figure out this is going down 6 and over 6. Ooh, that sounds like negative 1. So g double prime is negative 1 of 4. Now what about g double prime? This one's easy. At negative 2. Well, what's going on there? Remember we noticed that it had some corners in it? At negative 2, there is no slope, so it does not exist. The derivative does not exist due to a corner at negative 2, 2. You know, I don't know that you necessarily have to give a whole corner information, but hey, why not? And we have 2 more parts here. On what intervals, if any, is the graph of g concave down? Okay, so remember g prime? Well, let's just say this. G double prime, we already found, didn't we? That was just f prime of x. So when are we concave down? When the second derivative is negative, or when the first derivative is decreasing. Now I've got the second derivative. I'm talking about this side right here. So when is the second derivative negative, or the first derivative, meaning this, is decreasing on intervals. Now these are going to be x values from x equals negative 2, that's right here, from here to here, union, and then from here, which is 2, all the way to 8. So that's when this thing is, just check and make sure I got that right, and I did. And they also have here, make sure that you say your reasoning is g prime is decreasing on intervals. Okay, you could even say, so g is concave down. You don't have to say that, but all right. Letter D. The function h is defined by g of this other function. Find the first derivative of that thing. So h prime of x would be g prime composed of x to the third plus 1, but then multiplied by 3x squared. That's that chain. Okay? So g prime, remember up here? Let's go back up here. G prime is 2 plus f of x. So this would be 2 plus f of x to the third plus 1 times 3x squared. Now we are finding h prime of 1. So this would be 2 plus f of 2 times 3. Now f of 2, so our f function, remember, is the graph that we're looking at there, right? Yeah. So we should be able to read that off of there. Equals 2 plus, so f of 2 would be 3 times 3. Now I lost a parenthesis here, so this is important right there. You were probably screaming at your computer right now, right? So there should be parentheses there, which means there should be brackets right there, because all of that represents that g prime of x to the third plus 1. And so we end up getting 15 as our answer. And that's what they have here on the key. All right, make sure you show all your work here, and hopefully you got all this right. All right, I'll put together another video with these last 2 questions, and that'll wrap it up for this test. Good stuff. Let's wrap up our adventure of looking at this 2014 released AP Calculus AB exam. These are the last 2 questions on the No Calculator Allowed section. The free response, numbers 5 and 6. So let's look at number 5. We have a particle that is moving on an x-axis. So you can think about it going left and right at time t according to this function. First question just says, is the particle moving left or to the right at t equals 1? So what are we going to look at here? The first derivative, because the first derivative tells us direction, right? It would be the velocity. And if the first derivative is positive, we know it's going to the right. If it's negative, we know it's going to the left. So let's find the derivative. X prime of t would be velocity, by the way. And that would be 15t squared minus 18t plus 0. Just doing that power rule. You plug 1 in here. T equals 1, t equals 1. You get 15 times 1 squared minus 18 times 1. Boy, that sure looks like negative 3. That sure looks like negative 3. Now, is that positive or negative? Well, that's an easy question, right? That is negative, so this thing is moving to the left. So the particle, you always have to actually conclude by stating your answer. The particle is moving to the left since x prime of 1 equals negative 3, which is less than 0. And that should be enough to do it. Yep, I'm looking at the rubric, and sure enough, that's exactly what they want you to say. All right, at what time t, let's look at the next question here. At what time, I'm looking down here, at what time t is greater than 0 is the particle furthest to the left? So let's take our velocity, our x prime function. It's 15t squared minus 18. Let's find the critical values, like where it changes sign if it does, and that'll be when it turns around. When velocity changes sign, the original object must have turned around. So we're going to set this equal to 0. You factor out a 3t, right, and that leaves behind 5t minus 6. So t equals 0 is a critical point, and so is t equals 6/5. Right, so you now need to determine whether it's going left or right. Now we already set up above, right up here, we said at 1 it was going to the left. Okay, let's try a bigger number, like after 6/5. if you plug 2 or 5 or whatever in here, what ends up happening is you get a positive number. Okay? So, since x prime is less than 0 for t equals 0 to t equals 6/5, the particle is moving left. For t greater than 6/5, the particle is moving right. So, at t equals 6/5 is when the particle is furthest left. And I know I wrote a lot there. You could probably summarize that a little better. But you have to really lay out your reasons for that. Since the derivative is negative from 0 up to 6/5, and then from 6/5 to infinity, the derivative is now positive. So then it's moving to the right. So it must have been furthest to the left at 6/5. Now notice in the question, it doesn't say how far to the left does it go. It just wants the time. So don't do extra work here. They just want the time. Okay, question C. A second particle, y, moves along a y-axis, up and down, all right? So that the position at time t is given by the function here. At any given time, the origin and the positions of the particles are in the first quadrant alone. Find the rate of change of the area of the triangle. So you got a particle up here that's operating according to y of t, and then, of course, the stopwatch is ticking, right? And the same t is down here. This is x of t down here. This forms a triangle in the area of the triangle. So the area of a triangle would be 1/2 base times height. 1/2 base times height. We have to find the rate of change of the area. See, so that's a prime at 1 equals question mark is what they're asking us to do here. So we have to take the derivative of this. And this will be 1/2 times the first times the derivative of the second. Now remember, we did the derivative of the second up above here, and that was 15t squared. 15t squared. I got to go ahead and put y of t in there. 15t squared minus 18t. And then plus, we'll put the 1/2 there again, the derivative of y, so y prime is 7 times the original function, way the heck back here in the original problem, 5t squared, or t to the third, plus, here I'm going to just copy this, my short-term memory is just horrible. I'm going to paste that down here so I can see it. This would be 5t to the third minus 9t squared plus 7. All right, let me move all of that to the left so that you can actually see what I'm doing, right, on the screen here. There we go. All right, so I had to do the product rule. The product rule. Don't forget the 1/2 on the second side. Now, do I have to spend a lot of time doing algebra here? No, because they are asking us to just plug in t equals 1. Now that we've done the calculus, we can plug in t equals 1. So we get 10 times, so a prime of 1 equals 1/2 times 10 times 15 minus 18. See, they chose the number 1 because it ends up working out relatively well, times, and then we have 5 minus 9 plus 7. So this is 15 here. Actually negative 15. Always do those calculations twice. This is negative 3 times 10, that's negative 30, divided by 2 is negative 15. Over here we have negative 4 plus 7. Negative 4 plus 7 is 3. So this would be plus 21 halves. Okay, so that would be negative 30 halves if you're doing this in your head, right? You can't use a calculator, so you just be careful. We put all this time in this. We want to get it right. This would be negative 9 halves. Negative 9 halves. Now, do we have any units in this problem that we need to use? I don't see any. So, according to the rubric, that's what we need to do. Just show our work. The rubric says showing the area function. That's this right here. And then it says the derivative, the two derivatives. So I showed my 2 points for the derivative. Here's the derivative that they're looking for, and then the third point for the answer. Right? And that's part D, or part C, I mean. Not too bad. All right, question number 6 here. Consider the diffie-q, the differential equation that's given. And then, of course, f of x, y equals f of x would be the particular solution to the diffie-q, with the initial condition where 1 turns into 2, 1 comma 2. That point will allow us to solve for c when we're solving the differential equation. Find the slope of the line tangent. Well, remember, this does mean slope right here. So we have the slope machine or expression. All we have to do is plug in. We just have to plug in 1 and 2. So this would be 1 minus 2 over 1 times 2 minus 1. That all looks like that would all be negative 1. And that is the correct answer. See how easy that is? So the slope is right there. All right, on the axes provided, do the slope field. So I'm going to copy this here so that I can bring it down here and talk to you about it. All right, so here's my function, or at least my derivative, right? So we're going to do all these things. Do you notice some things that I start to look for is that I see that at y equals 1, all the slopes are 0. So I would put a horizontal here, and here. Now, one question is why aren't there dots here? Because you're not allowed to plug 0 in. It doesn't exist there. So there is no derivative there. Okay, so then let's keep going. What about if we plug x equals 1 and y equals 0 in? That would end up being negative 1. So that would be positive 1. So right here, let me erase my circle, we would put a positive 1. Now let's plug 2 in for x, and y is still, so 1 minus 2 over 4, y is still 0, so we're still going to get a negative 1 here. Okay, so that would be negative 1/2. So if you go to the right here, did I get the wrong sign? That would be positive 1/2, or negative. Let's see. 1 minus 2 is negative 1 times negative 1, so that one was right. And then 1 minus 1/2 is positive times a negative. I think we're good. I think we're in good shape. This is negative 1/2, which means this would be sort of like this right there. And I just looked at the answer, and that's right. I didn't want to look at the answer until after I checked it. My spidey sense was going off, my mathematical spidey sense, I like to call it. All right, so let's now plug in x equals negative 1. So that would be 1 minus 2 over negative 1 squared, once again, times negative 1, because we're plugging in negative 1 comma 0. So that would be 1 minus 2, which is negative 1. So that would be positive 1 again. So right here, we have a positive 1. Okay. Now, let's continue on. What about 2 comma 2? That would be this point right up here, 2 comma 2. So we plug that in, 1 minus 2 over 4 times 1. Well, that's a half, so that's going to be up like that. What about plugging 1 in? 1 minus 2 over 1, all times, I'm doing 2 minus 1 again, so y is 2. So times 1, that's negative 1. So we're down like that. We have one more dot to do. We need to do this point over here. That's negative 1 for x. So that would be 1 minus 2 over 1 times and then it was our y value there is 2, so 2 minus 1 is 1. So that's negative 1. So it would look like that. All right, I noticed that we had some symmetry on the left compared to the right. Right, and that's another thing that you can start to notice, but it was not so hard to brute force that, honestly. All right, moving on to number C. We are almost done. Part C. Find the particular solution to the differential equation. So this is where you're going to actually solve it by doing an antiderivative. And how do you do this in a case like this? You do separation of parts here. So we're going to move the y minus 1. We're going to divide both sides by y minus 1 is what we're doing. And all of that equals 1 minus 2 over x squared dx. So you get 1 point on the AP exam for writing that, for separating your variables. Now we're going to integrate both sides. This is the natural log of y minus 1 equals x. All right, so the exponent here, this is 2x to the negative second, is what this is right here. So we have to add 1 to the exponent, that's negative 1, divide by the new number, so we get minus 2, but it's going to become plus 2 because of this already minus, right? Plus 2, and it's going to be over x. And then plus c, plus c. All right, so you get a point for doing that. Now we're going to solve for c. We use the initial condition here. So we plug 1 in for x. We plug 2 in for y. Plus c. So the natural log of 1 is 0, because anything to the 0 power is 1, equals, this is 3 plus c, so c equals negative 3. All right, so you go ahead and write that in. The natural log of the absolute value of y minus 1 equals x plus 2 over x minus 3. All right, now what do you do? Now what do you do? Are we done? It says find the particular solution with y all by itself. So the last point here, I'm looking at the rubric. To get the final point, to get the 6th point here, we have to solve for y. And the way you do that is a base e. You put a base e on both sides, you're left with y minus 1 all by itself. So then if you add 1 to both sides, you get 1 plus e to the x plus 2 over x minus 3 power, and that is what we call the particular solution. And that is the correct answer. I'm looking at it here on the rubric. We got all 6 points. All right, hopefully you found this video and all these videos in the playlist and into the compilation video useful. And check out my other videos to help you review for the AP exam. All right, good luck. I'll catch you later.